We present the Intrinsically Guided Exploration from Large Language Models framework, short for IG-LLMs. IG-LLMs explores a promising avenue for guiding robotic exploration efficiently, particularly in highly intricate, long-horizon robotic manipulation tasks where conventional methods may face challenges. IG-LLM's novel future includes utilizing large language models as an assistive intrinsic reward, guiding the exploratory process of conventional reinforcement learning in intricate robotic manipulation tasks. Let us first look at it from a biological perspective. To us humans, completing long, complex, and sequential tasks appears to be requiring minimal effort. Amongst numerous biological advantages we humans possess, one of our main approaches of eliciting meaningful reasoning is through language. However, from a learning perspective, this is notably challenging. Sequential, long-horizon robotic tasks, for instance, present a daunting area. How can we now take these biological principles, as seen in humans, and endow intelligence with the same reasoning in such complex tasks? The essence of the challenge in reinforcement learning lies in the necessity for exploration, a journey through an environment where feedback is minimal, not readily apparent, and typically comes in the form of sparse rewards, namely the challenge of exploration. This begs the question, how can we overcome these challenges? One could, for instance, induce specific handcrafted dense rewards to overcome these challenges. In this way, immediate feedback from the environment can overcome the challenges of attaining a terminal sparse reward. Unfortunately, this necessitates notable engineering efforts and is most importantly rendered very task-specific, significantly limiting the ability to generalize across various tasks and environments. A promising alternative in overcoming some of these exploration challenges lies with intrinsic rewards, which can be densely represented alongside the sparse extrinsic one from the environment as per the reinforcement learning paradigm. Nevertheless, while current intrinsic methods have shown promise, these methods still struggle with increased dimensionality problems, with a notable example shown here, where in a seemingly simple, grid-based environment, the exploration necessitated becomes all the more higher as the grid space is expanded. While these methods may perform well in simple two-dimensional settings, in higher dimensional space, these approaches can lead to drifting away from the main objective of the task at hand, while attempting to explore areas which are not directly relevant to the final end goal. So what alternatives do we have? In the quest for more effective exploration strategies, the emergence of large language models represent a promising avenue in harnessing the power of language as a form of reasoning. Nevertheless, the integration of large language models is not without its challenges. Even with their impressive capabilities, large language models can sometimes get things wrong or suggest actions that don't quite fit the task at hand. Essentially, their outputs cannot be assumed to be correct. Imagine now giving robots the ability to think and reason just like us, using vast amounts of language understanding. Large language models can provide hints which actions might be worth exploring. That's where IG-LLM steps in. We're blending the strengths of large language models, building upon intrinsic learning, leveraging the traditional reinforcement learning paradigm, and aiming to derive more efficient and effective exploration strategies in notably complex long-horizon tasks. IG-LLMs seeks to harness large language models not as a standalone solution, but as to complement traditional reinforcement learning via effective and efficient exploration techniques. By utilizing large language models as an assistive intrinsic reward mechanism, our framework aims to navigate the pitfalls of both sparse rewards and the inherent limitations of large language models. As part of our evaluation, we put IG-LLMs and other state-of-the-art learning approaches to the test in two main environments. First up, we dive into the deep sea environment, a grid-based challenge that serves as our testing ground for evaluating exploration strategies in reinforcement learning. We start the evaluation from a straightforward 8x8 grid, expanding to 64, 128, and finally to a massive 192 by 192 grid size. With each expanding grid size, the probability that the agent will always be taking the diagonal down-right actions decreases significantly. Diving right into it, initially, most methods, including traditional reinforcement learning, seem to cope well. However, as we ramp up the complexity by expanding the size of the grid, traditional approaches begin to falter. It's here, in the challenge and complexity of the environment, that the strengths of our IG-LLMs appear to show, demonstrating not just resilience, but also the ability to thrive where other state-of-the-art methods struggle. Transitioning now to the main environment, we take on a notably complex, long-horizon sequential task in robotic manipulation. Roman is in its core a hierarchical learning architecture. This means it uses a collection of experts trained to handle specific actions, or in this case, macro actions. These actions are complex tasks in themselves. By evaluating IG-LLMs and other methods on Roman's hierarchical learning architecture at the highest level, namely its gating network, we evaluate the ability of these methods in orchestrating the correct activation of Roman's intricate number of experts to achieve the long horizon end goal. Starting with case 1, we observe a simple task necessitating the activation of a single macro action. Here, all methods perform well. Moving now to case 2, the complexity slightly increases. Despite the added challenges, all methods continue to exhibit success. In case 3 now, the task complexity escalates. Reinforcement learning with random network distillation starts to show signs of struggle, forgetting the vial during the task execution. As we advance to case 4 now, the cracks widen for traditional methods. Reinforcement learning, with or without count-based exploration or random network distillation, appear to falter, unable to successfully manage the task. Case 5 now overpowers reinforcement learning, with or without count-based exploration or the inclusion of random network distillation. IGE-LLMs, alongside the direct usage of large language models and reinforcement learning with the intrinsic curiosity module, still perform well. The penultimate challenge now, case 6, ups the ante with 6 macro actions. At this level of complexity, all methods except for IGE-LLMs fail in meeting the intricate demands of this task, showcasing the significant advantages of IGE-LLMs. Arriving finally in case 7, which represents the peak of complexity, demanding a sequence of 7 macro actions. This ultimate test witnesses the failure of all methods compared except for IGE-LLMs. Our approach stands alone in its success, underlining its superior ability to handle the most complex, long-horizon tasks within the Roman environment. Collectively, our results show and underline IGE-LLMs as a promising framework in providing the guidance needed, leveraging the context-aware reasoning capabilities of large language models, and providing effective and efficient exploration strategies. This integration showcases a promising path forward in making robots more adept at navigating highly intricate sequential tasks commonly seen in long-horizon robotic manipulation settings.